Hi, welcome to Chemical Formulas Review Part 2. Today this review is going to focus on naming ionic compounds. So first we're going to review a little bit about ionic bonding. We're going to talk about naming binary ionic compounds. We're going to look at naming ionic compounds with transition metals. And finally we're going to talk about how to name ionic compounds that also have polyatomics. And in the process of looking at the polyatomics, we'll also bring in some examples where we have both a transition metal and a polyatomic existing within the same compound. So what is an ionic bond? Ionic bonding is the full transfer of electrons to form positive and negative ions. Typically in this course we're going to see it happening between metals and nonmetals, and they're held together by electrostatic forces. And remember, an electrostatic force is just that positive, negative force of attraction that's going to hold an ionic compound together. So if we look at this little animation over here, this little blue sphere is representing my metal, and this little red sphere is representing my nonmetal. Nonmetal. So when a metal loses an electron, there it is, it's losing its electron, the atomic radius is going to shrink. So now I have a smaller ionic radius than atomic radius, and it's going to have an overall positive charge. At the same time, when this nonmetal gains an electron, the radius is going to increase, and because we're gaining an electron, we're going to have an overall negative charge. Now where we see this occurring is between elements. Let's take potassium. When it loses its one valence electron, it becomes positively charged. And bromine, when a bromine atom gains an electron to get its full octet, it's going to be negatively charged. So it's that positive negative force of attraction holding these ions together that's really forming our ionic compound. And again, we refer to that force of attraction as an electrostatic force. So now let's discuss this little abbreviation right here, IUPAC. Now according to the New York State Core Curriculum for Chemistry, a chemical compound can be represented by a specific chemical formula and assigned a name based on the IUPAC naming system. And sometimes in Regents questions, we see this little abbreviation right here. Some might ask, what does that mean? Well, IUPAC means the International Union of Pure and Applied Chemistry. And really all that is, it's just the standard method of naming chemical compounds that New York State uses. So everything is systematic across the exam. Don't be distracted if you see IUPAC in a question. It's just the standard by which all chemicals are named. So now let's talk about naming binary ionic compounds. So remember, binary means two. Ionic means that we're going to be involving a positive and a negative ion, and we're going to be making a compound. So two or more different elements coming together. So when you name a binary ionic compound, you want to start out by naming the positive ion first. Now in this course, typically the positive ion is going to be a metal. And it's also, at the same time, the less electronegative element. We can always go to table S to determine the electronegativity of different elements. And when you write the name of the first part of the compound, we're not going to modify the element name. So here I have a picture of strontium. So I know the symbol of strontium is Sr, and then if I spelled out the name of it, it would be Stronium, strontium. Then we have to look at the second part of the compound name. So write the name of the negative ion second. Typically in an ionic compound, the second element listed is going to be a nonmetal, and concurrently the more electronegative element. Now what we're going to do here is we're going to take the element name, but we're going to modify it. Most elements on the periodic table, not all, but the majority of the nonmetal elements on the periodic table are going to end in INE. What we're going to do is we're going to change that ending so it ends in IDE. So here's my strontium, and I'm going to combine that strontium metal with fluorine gas. So fluorine has a symbol of F, and if I spelled it out, it'd be fluorine. So fluorine ends in INE. So now I'm going to combine these two elements together. Let's put a little plus sign up here. And we're going to make this new compound. And this compound symbolically is represented as SrF2. So if I was to name this, I'd take the first element, which is strontium, and I'd just say, hey, I'm strontium. That's the first part, and I'm not going to modify it at all. But for the fluorine part, again, I'm going to take that INE ending and change it to IDE. So here's the second part of the compound name. So strontium fluoride. So it's that IDE ending that's saying it's the more electronegative element, and in this case, the nonmetal. Now let's talk about naming ionic compounds with transition metals. Now if you recall, if you look at your periodic table, the transition metals are going to be located in groups 3 through 12, and these are the elements that are typically, and not all of them do, but typically going to have more than one positive oxidation state. So if you look at a symbol on your periodic table, you're going to notice more than one charge in that upper right hand corner. To represent a transition metal that's going to have more than one positive oxidation state, we needed to use Roman numerals. So a Roman numeral is used to symbolize the specific, very specific, positive oxidation state of the transition metal in the formula. Now, in case you never really learned your Roman numerals beforehand, now is a good time. So a Roman numeral number 1 is represented basically as a capital I. 2 is represented as two I's together, and sometimes we'll just see it as represented like this. Roman numeral number 3 is 3 I's, or again, like this, 1, 2, 3. 4 is basically IV, so again, I could just represent it like this, instead of separate it out like this. 5 is just a capital V. And 6, what basically has happened here is I take this I that is on the left-hand side and I'm going to switch it over to the right-hand side. So another way of representing this could just be like so. If I wanted to do 7 for some reason, I could do something like this and I'd add on, so it's 5, 6, 7, or 8. Goes like this and this. I personally have never seen a Roman numeral number 9 or 10 represented, so I'm just going to go up to 8. Now, in order to figure out what Roman numeral you need to use, the first thing that you need to do is look at your chemical compound and then determine, are you using a transition metal? And if you're using a transition metal, assign oxidation numbers. Now, it's always good practice in general to assign oxidation numbers to the elements in your chemical formula, but it's going to be critical, especially if you're using a transition metal. So what I'm going to do here is I'm going to say to myself, all right, what do I have going on here? Well, I know oxygen is -2. I know this is going to be electrically neutral. I know that these are in a 1-to-1 ratio. So if oxygen's -2, iron here has got to be +2. So when I write out the chemical name of this, it's going to be iron, Roman numeral number 2, oxide. Again, it's oxygen. That's not a typical nonmetal that's going to end in INE, so I've got to modify it again so it ends in IDE, so it's iron 2 oxide. So if I look at this +2 right here is being represented by this Roman numeral right here. Let's look at some more examples. Let's look at Cr2S3. So I know this is chromium and sulfur. So if I uncrisscross this, this 3 is going up here, so chromium is going to have a charge of +3, and this 2 is going up here, so sulfur has a charge of -2. Now again, I'm only interested in using Roman numerals with my transition metals. If I look at chromium, and chromium on here has multiple oxidation states, so I'm going to write this out as chromium 3, Roman numeral number 3, sulfide. So this +3 right here is represented as a Roman numeral 3 right there. Let's look at another one. I have titanium and I have chlorine. So if I uncrisscross this 2 is coming up here to be +2, and there's an assumed 1 right here, so if I uncrisscross that, chlorine, if this is positive, chlorine has to be negative, so that's going to be -1. So when I write this out, it will be titanium, Roman numeral number 2, chloride. Chloride. And again, when I look at this +2 right here is represented by that Roman numeral 2 right there. Now let's look at my last example right here. I would pick out the element that is one of the most difficult ones to spell, but remember, you can always go to table S and check your spelling. So I have Mn3N4. So this 3 has to be coming from the nitrogen. So nitrogen is -3 because it's listed second. And the 4 is coming from the manganese, which is right there. So that is going to be manganese. And this is +4. So Roman numeral number 4. And then nitride. Nitride, because it's just a nitrogen by itself. It's not a polyatomic. It's not nitrate. It's not nitrate. It's a single nitrogen by itself. So again, we have that IDE ending. So now let's talk about naming ionic compounds with polyatomic ions. Now, remember, you have your reference tables when you take the exam. Some teachers might recommend that you memorize the polyatomic ions. That's absolutely fine. Go on to AP Chemistry. You're in great shape. If your teacher doesn't require you to memorize the polyatomic ions, then always remember that all polyatomic ions used on the Regents Chemistry exam can be found on Table E. So you've got to know your polyatomic ions well enough to recognize them in a formula, but in general, for the Regents exam, you don't need to memorize them. If you're given the formula name and it doesn't end in IDE, if you're looking at your chemical formula and you're saying, it's ending in ATE or ITE, always good to go to Table E and look up and find out the exact spelling of your polyatomic ion and the formula that goes along with it. There are 2 exceptions. Hydroxide is an exception, OH-1, because it does end in IgE, but we use hydroxide a lot in this course. And then cyanide, which is CN-1. It also has an IDE ending, but it is a polyatomic. So let's look at our 2 examples here. I have Fe, which is iron, which I also know is a transition metal, so I have to be careful because the name needs a Roman numeral if I'm dealing with a transition metal. And then this NO3. NO3 is a polyatomic. It's nitrate, so I can look that up on Table E and make sure that I have my spelling correct. So Fe is iron, so I'm not going to modify that at all. So iron. I know that this 3 is coming from the Fe if I uncrisscross it. So this is Fe plus 3. There's an assumed 1 down here, which means the charge on the NO3 has to be -1. So this is iron, Roman numeral number 3, nitrate. And when in doubt, always go back and check. It is always worthwhile to go back and check and make sure that everything matches on your periodic table and your Table E. Let's look at this next one. I have CO, which is cobalt, another transition metal, and SO4. If I look up SO4 on Table E, I know that's sulfate. Sulfate has an overall charge of -2. And remember, these are ionic compounds. I'm going to have a positive ion and a negative ion. And remember, this SO4, just like the NO3, is held together by covalent bonds. So if I had to say, how would I classify this compound in terms of bonding? Well, this would have both ionic and covalent bonds. The ionic bond is between the positive metal ion right here and then the negative polyatomic. So the SO4 as a whole is -2, which means the cobalt ion here has to be +2. So when I write this out, it'll be cobalt, Roman numeral number 2, sulfate. And again, this +2 ion is represented by that Roman numeral right there. And the SO4 is represented by the sulfate, and that's on Table E. Let's do a couple more examples. Li2CO3. Now, Li is a group 1 metal. I know that the charge on Li is +1 because it's found in group 1. Lithium is not going to need a Roman numeral. So if I know that, then I just look at the CO3. I say that's a polyatomic. I look it up on Table E. I make sure I have my spelling correct. So when I'm writing this out, it'll just be lithium carbonate. Lithium carbonate. No need for a Roman numeral because lithium only has 1 valence electron and therefore only has a +1 charge. Let's look at this next one. Barium. Barium's in group 2. Again, we don't need a Roman numeral here because if you look up barium on here, only has 1 charge affiliated with it, which is +2 because it has 2 valence electrons. So again, no need for a Roman numeral. Then I go to Table E. I look up PO4. I find that that is phosphate. And it makes sense because if I uncrisscross this 3, PO4 has a charge of -3. I uncrisscross this 2. Ba has a +2 charge. So therefore, everything's matching up. So when I write this out, it's just going to be barium phosphate. Now we have lead. Now lead doesn't fall into the transition metal section, but it does have multiple charges. If I look up lead on my periodic table, I can see that it can be a +1 or a +2. So again, to determine the charge on the lead ion, I'm going to take this 2 and I'm going to uncrisscross it. So it's going to be Pb +2. The hydroxide I know is -1, which again I could go through all the calculations to make sure that this is electrically neutral. So I would say, all right, Pb is lead, Roman numeral number 2, and then the OH is hydroxide. Again, one more time, this +2 right here is represented by the Roman numeral. So I look at everything that I have here, and I have lead, I have the Roman numeral, and I have the hydroxide. So what did we learn in this review? We went over ionic bonding one more time. We talked about how to name binary ionic compounds. We talked about how to name ionic compounds with transition metals. And finally, we talked about how to name ionic compounds containing polyatomics. Need more help? Feel free to contact me, and I'm always looking for feedback. Hope you have a great day.